Share with you at first. So the first thing, the information that the smallest unit of the binary bit we already know, and any 8-bit unit is, and that byte can be split into two groups of each 4 bit, and if it is split into 4 bits, then it is called nibbles. And byte can also be grouped into words. And the term words in the computer terminology, there are two different meanings. In case of memory, the word means a group of bytes or bits. So whenever we actually usually it's an amount of bytes, because 1 byte means 8 bits, right? So the minimum is the 8 bits we can consider. So the word is actually a group of bits or bytes, as you can mention. So here, when we talk about this storage or memory, each storage element here, this you can see the element here, the block, each block is known as a cell. Each storage element in a memory is known as a cell, and each cell can contain only 1 bit, either 0 or 1. We already talked about our random read-only memory in our last lectures. So inside the block diagram, we see how those bits are actually arranged, how we can design by using the mouse each cell, right? And then we can store either 0 or 1. So these memories are made of arrays of cells, not only one cell, memories are arrays of cells, and is illustrated in figure. And this is an example for 64 cells. So these 64 cells can be mentioned or can be designed in different categories. Like, for example, 8 by 8. So it is also 64. In the columns, we have 8 cells. In the row, we have 8 cells. So it is also 64, 8 by 8. This 64 memory cell can be organized by 16 into 4. That means it's a nibble, right? We can split our 1 byte into 4 bits, and then we call it a nibbles. So 16 into 4 means a 16 memory locations, and each location has 4 bits, or a nibble. Or it can be 16 by 1. That means it is a 64-bit memory, and the memory cell is identified by the number of words it can store here. Okay. So if we just want to represent a very small chip of this memory cell by 8 by 8 memory cell, here you can see. In the row we have 8, and in the column we have 8 cells. So this is an 8 by 8 memory chip, that means a 64 memory chips here. And the location of unit of data in a memory array is called the address. So we have to find the location. Each location of this unit of this memory cell is known as address. So here the address of a bit in the 2-dimensional array is specified by the row and the columns. For example, they mentioned that address of the blue bit is the row 5, column 4. Here, the address for this case, it is just only for row 5, column 4. But in this case, the address is the blue byte for 1 byte. It is just only row 3. So this is how we can address. Why this address is necessary? Addressing is the process of accessing the specified element or the location in the memory. Since the memory stores binary data, data must be put into our memory, or it should be copied from the memory. Either we write it, put into the memory, or we read it or copy from the memory when needed. So the write operations put the data into the specified address in the memory, and the read operation copies the data out from the specified memory. And data that we are trying to retrieve or we are trying to put into the memory cells, we should use through a set of lines that is known as data line. So we have to use these data lines to read or write the data from the memory cell. And those data bus are bidirectional, so that we can read and write as well. That's why their data line should be, of course, be bidirectional. In case of byte organized memories, the data bus are at least 8 bits. Of course, right? Byte organized means the one word consists of 8 bits. So there will be at least 8 data lines to get the byte organized memories. For a write or read operation, an address is selected, placing the binary code 101, 011, 0000, 111, whatever. The placing the binary code represented the desired address on a set of line called the address line. So there is one is data bus, one is the address bus. In the data bus, that is the bidirectional, but the address bus is not a bidirectional. It's only one directional. We just need to send the address. The address code is decoded internally and the appropriate address is selected. So we already saw in our last lecture when we talk about the read-only memory, a decoder circuit, a 1 into 8 or 3 into 8, 16 decoder, 1 into 8 decoder. We have to have a decoder circuit so that will decode the binary address code. In case of multiple array memory figure, there are 2 decoders and one for rows and one for the columns. So this is the single array memory and this is the multiple array memory. In case of multiple array memory, we can use a decoder circuit for row as well as the decoder circuit for the column. Okay. Now this is the very simple, the write operation and the read operation. This is the write operation. So that means we want to write something in our memory cell. So at first we need to know the address, the location, where you want to store your memory. The simplified write operation is illustrated in this figure. To store a part of data in the memory, a code held in the address register is played on the address bus. So the code of the address will be in the address register. From the address register, that code will be given to the address bus. And the address bus will decode with the decoder circuit to a specified location. Then once we get the location, then the memory gets write command. And then the data byte held in the data register is placed on the data bus and is stored in the selected memories. So this is a very simple one. We can draw the circuit like this. So this is the SD decoder, a decoder circuit. This is the address register. Address register will contain the address and it will give it to the address bus. The decoder circuit will choose, for example, it is 101. So 101 recorded to 5. So it will specify the address. And then the write command will be given. And from the data register, the data will be given to the data bus and it will be write into the specified memory cell. So this is a very simple write operation of the memory cell. Similarly, this is the read operation. If you want to read, at first we need to know the address. On the same process, the code held in the address register is placed in the address bus first. So once the address code is on the address bus, the address decoder will decode and find the specified memory cell or the location in the memory. The memory then gets a read command and a copy of the stored information will be selected and give it to the data bus or placed into the data bus. And from the data bus, it will goes into the data register. So this is the simplest data read operation. So as I mentioned, these are the information I just copy and paste from our reference book, but these are the very basic information about the read operation, about the write operations of the memory cell. Okay. Now we'll go to the whiteboard. We want to talk about these more in details about those RAM circuit. In our last lecture, we talked about the read-only memory, right? Today we'll talk about what's happening. Is there any sensors? Today we'll talk about the random access memory. Basically, there are 2 different kinds of random access memory. One is known as static RAM, another is known as dynamic RAM. In short, we call it SRAM and DRAM. So there are 2 different kinds of RAM. One is known as static. Another is known as dynamic. There are of course a difference between this SRAM and DRAM. So let's try to get those differences. For example, this is SRAM and here we talk about DRAM. And for the usage, we use this SRAM in the memory but as a cache memory. That means they are temporary. The processor want to use randomly or what I can say?
Upload the buffer.
Upload buffer and also frequently, it want to use repeatedly. So they just put into cache. So they are temporary. So these are cache memory. As for usage, so if I mention about the usage, it is for the cache memory and DRAM is used for the main memory. The second difference between these two is the speed. The SRAM is the fastest among all the memories. Among all the memories. If it is a ROM or RAM, the SRAM is the fastest among all the memories. DRAM is slower than the SRAM, faster than the others, but slower than the SRAM. So it is fastest or fast, and it is slower than SRAM. Speed. If we talk about the cost, it is costliest among all the memories. Why we'll see later, when we'll see the construction of the structure, internal structure, we'll see why it is the costliest. It is the costliest. And it is less cost than the SRAM. About the density, it has lower density. Lower density, it has higher density than SRAM. About the power consumption, it has less power consumption than the SRAM. So it is higher power consumption than SRAM. So these are the few differences between the SRAM and the DRAM. And we'll
Power consumption is lower.
then yeah, it is higher. So we'll see, and whenever we'll see the internal structures of SRAM and DRAM, then it will be more clear to us why it has lower density, why it is more costlier, and why it is the power consumption is high. So let's start with the DRAM, internal structures of the DRAM. I will give it the handnotes. In the handnotes you can see these differences also. The DRAM, a single cell, a 1 bit of DRAM consists of one transistor and a one capacitor. It consists of a one transistor and a one capacitor. The structure, internal structure of DRAM. It consists of a transistor, a MOS transistor, and a capacitor. And then this transistor is connected to, this is called word line, and this is called input line. This is the capacitor, and this is the transistor, a MOS transistor. This transistor is known as pass transistor. The pass transistor is nothing but it acts like a switch. It just allows the signal to pass it from one source to drain to source. It's like a switch. So this transistor is known as a pass transistor, so that we don't need to connect the power supply directly here. the MOSFET is acting like a switch here. So here memory bits are stored in terms of charge across the capacitor. Here the memory bits either we have to store 0 or 1, right? Here the memory bits are stored in the memory cell in terms of the charge across this capacitor. So by charging or discharging, we can either store 0 or 1. Let's see the operation here. So in the DRAM cell, we can access the capacitor by using the pass transistor, right? If you want to access, because this is my bit line. From here we can either give 0 or 1, or we can read 0 or 1. So we have to access this bit line. So in this DRAM cell, we can access this capacitor through the MOS capacitor. So that means we need to turn on the transistor at first. When the transistor will turn on, then we can access this capacitor. For example, this is the gate, we already know. So this is the drain, this is the source. So when the gate has sufficient gate voltage, then this transistor will turn on. When the transistor will turn on, then the channel form and the capacitor will charge or discharge through this way. So we can say that in the DRAM cell, we can access the capacitor by using the pass transistor. When the pass transistor is turned on, then we can read the capacitor data or we can write into the capacitor. So when the pass transistor is off, what will happen? The charge across the capacitor will remain as it is. So for example, if you store 1, there will be charge. Now if the pass transistor is off, the charge supposed to be there as it is. That means we have to store 1. But in practical, ideally it's supposed to be there. But in practical, there is some leakage current. And due to that leakage current, this charge in the capacitor will gradually decay. To overcome this issue, we need to give some periodic refresh cycle. We have to apply some periodic refresh cycle. That's why it is known as dynamic RAM. In case of static RAM, it will be static. The charge will remain there. But here, due to the leakage current from the gate terminal of the MOSFET, ideally the charge should be there when the transistor is off. But even the transistor is off, due to the leakage current, this charge will decay gradually. So when the charge will decay gradually, this stored logic 1 will become logic 0. So to retain this logic 1, we have to do some periodic refreshing cycle. That's why it is known as dynamic RAM. Okay? So now, if you want to read the data or read the information from here, that means we are talking about the read operation. What do you need to do? Of course, at first, we have to turn on the transistor. To turn on the transistor, you have to apply a sufficient gate voltage. Or here, we call it a word line voltage. So, it can be turned by applying voltage to the word line. We have to apply some voltages here to the word line. When we apply the voltage to the word line, it will be enough voltage, that is enough for the more than the threshold voltage, then the transistor will turn on. And once the transistor will turn on, then the stored charge in the capacitor will be available at the bit line. So we have a stored charge. For example, if it is a logic 0, for logic 0, 0 volt. For logic 1, for example, 2 volt. So when this transistor will turn on, the available charge, for example, if we have a logic 1, these 2 volt will be available at the bit line. Okay? So during the read operation, the capacitor will lose its charge, right? Because now capacitor is discharging here. Here we are increasing from 0 to 2 volt. It is decreasing. The charge is discharging here. So this type of read operation is known as destructive read operation. A destructive read operation because it is losing its charge. Again, to avoid that, we need to perform the refresh operation for after every read operation. Because it's not like that we just take the data, we don't need this same data next time, right? So we need to refresh it. The stored data was 2 volt. During the read operation, it is actually discharging from 2 volt to 0 volt. Then it seems it becomes logic 0. So it's not true. So that's what we need to done or perform refresh operation after every read cycle, so that the capacitor can get its original value or original voltage. For example, 2 volt for logic 1. Okay. So now if you want to increase, this is the very basic one. Now if you want to increase the speed of this read operation, what we can do? To increase the speed of this read operation, what we can do, we can give some initial voltage to the bit line here. For example, we already give some 1 volt to the bit line. We already applied 1 volt to the bit line. Now when we will go for the read operation, here, now it has to discharge from 2 volt to 1 volt, not 0 volt, right? So that's why it will take half of the time. So in this way, we can improve or increase the read time or the speed of the read operation. Okay. Another thing is that in this read line, there will be an amplifier. A sensing amplifier is connected here. It can sense any incremental voltage is there or not. For example, if we want to increment, because here it is 1 volt, but it is supposed to reach to how much? 2 volt, because the logic 1 is 2 volt. So if you want to read logic 1, it's supposed to be 2 volt. So it's supposed to go from 1 volt to 2 volt, it will take 10. But previously it was required to go from 0 volt to 2 volt. Now it is now going from 1 volt to 2 volt, we already reduced half of the time. Another way to speed up the read operation is that if we have some sensing amplifier here, it will sense any incremental changes. For example, when there is a change from 1 volt to 1.1 volt, so it can see the direction, whether it is increasing or decreasing. So any incremental sensing, it can sense and can amplify and can say that it is a logic one. So this is how also we can improve the speed. Okay. So here in this case, we actually call it, this bit line is pre-charged in some finite value or in some finite voltages. What about the write operation? During the write operation, that means we have to write something from the bit line to the capacitor. So during this write operation, all the bit lines, so this is only for one cell, right? So it is an array. If you just think about an array, so all the bit lines are pre-charged with some certain voltages. During the write operations, all the bit lines will be pre-charged in some certain voltages. For the particular bit line on which we want to write, the bit voltage is applied. So for example, this is one cell, then another cell, right? Then another cell. So if you want to write in this capacitor or in this memory cell or in this memory cell, the particular bit line will be given some charges. So for the particular bit line on which we want to write, the bit voltage is applied to that particular bit line. When the pass transistor is on, then whatever voltage is applied to the bit line will be charged to the capacitor. So if you want to charge logic 1, so you will give 2 volt here. If it is logic 0, you will not give any volt here. If you want to charge this one, 2 volt here. So when the pass transistor will turn on, the capacitor will charge up to 2 volt. This capacitor will not charge, and this capacitor will charge up to 2 volt. So we can write 1, 0, 1. So again, I'm mentioning during the write operation, all the bit lines are pre-charged with some finite voltage. For the particular bit line on which we want to write the bit voltage will be applied to that particular bit line. And then once the pass transistor will be turned on, whatever voltage is available to that bit line will be transferred to the capacitor, or the capacitor will be charged according to that bit line voltage. Okay. As you can see, this DRAM or dynamic RAM consists of a capacitor. So the charging and discharging of that capacitor actually influence the speed of this read and write operation of this DRAM, because there is a time, charging and discharging time. So even if you just recharge these bit lines, there is some charging and discharging time for each capacitor. So the speed of this DRAM depends on this charging and discharging of the capacitor. Now if I look into the internal structures of the SRAM, it consists of 6 transistors. Here the DRAM consists of only 1 transistor and 1 capacitor. On the other hand, the SRAM consists of 6 transistors. 2 transistors are for pass transistors, and other 4 transistors will make a cross-coupled inverter circuit. How it looks like? So it is something
Is this right operation?
sorry.
This is.
This is internal structure of SRAM. SRAM. So look at here. I'm sorry, maybe I'm not very good at drawing, but become very clumsy, but I'll try to make it clear to you. So this is transistor, 1 transistor. We can see this is another transistor. This is a transistor here, 1 and 2. This is another transistor, 10. So we can name it. So this is 1, this is 2, this is 3, this is 4, this is 5, this is 6. You can see here, it is nothing but the CMOS, PMOS and NMOS. Look at here, this is a bubble here, so this is a PMOS and NMOS. So if you connect your PMOS and CMOS together in series, it is a CMOS, right? PMOS and NMOS. Here it is a PMOS, you can see it's a bubble, and this is NMOS, so it's a CMOS. So this is a CMOS, this is a CMOS. And CMOS is nothing but an inverter circuit. It's a cross-coupled inverter. So as I mentioned, the SMOS consists of 6 transistors. Out of 6 transistors, 2 transistors, this transistor 5 and transistor 6 are known as pass transistors. These 2 are pass transistors. The pass transistors will connect the bit line to your memory cell. So we have to give the bit line here. So this is the bit line, BL, and here we have another bit line. This is inverting or bit line, BL bar. And this is similar, the word line, or in short, we just write WL. So this transistor 5 and transistor 6. Transistor 5 and transistor 6, T5 and T6 are my first transistor. Transistor 1 and 2, my CMOS, one CMOS. Transistor 3 and transistor 4 is my another CMOS. CMOS is nothing but an inverter circuit, right? So we can say remaining 4 transistors are the true cross-coupled inverter. True cross-coupled inverter. Cross-coupled inverter. So we need to connect here, it is connected to here. So if we just simplify it, we can simplify it to understand so that, so it is a CMOS, right? A CMOS is nothing but an inverter. This is a CMOS, is nothing but an inverter. So if I just remove this tube, you can see right? This is an inverter, and we can design an inverter with a CMOS, a PMOS, and an NMOS. So this is the simplified version. So inside this block, we actually have a CMOS here, we have a CMOS here. So to get a CMOS, we have 2 transistors here, 2 transistors here. So 4 transistors, 5 and 6. Okay. So in this SRAM cell, the memory bit is stored. Only one memory bit, either 0 or 1. In the DRAM, to store one bit, either 0 or 1, we have just one transistor. And here, how many transistors? 6. That's why the density is poor than the DRAM. Density is less. You require 6 transistors to store only one bit in case of SRAM. In case of DRAM, you just require only one transistor. That's why the SRAM is more costly, because you have to have 6 transistors here. These are the few reasons why they are less density and a higher cost. So now in this SRAM cell, the memory bit is stored between these 2 cross-coupled inverters, right? So if you want to just store 1, if you just store logical 1, that means here it is logical 1. So when it is logical 1, output of the inverter is logical 0. So this comes to here, then here output of this second inverter is again logical 1. So that means during the operation, here this 1 is circulating. This is another advantage. In case of DRAM, we need a periodic refresh cycle. Because when the capacitor discharges, we cannot have a logic 1 anymore. So we need to do the periodic refresh cycle. That's why it was known as DRAM, a dynamic RAM. On the other hand, if you look at here in the static RAM, the 1 is circulating. We don't require any extra periodic refreshing cycle. So already refreshing is there. It's circulating. 1, 0, 0, 1 is circulating. So from the structure also, it is very clear to us now why those are named as a dynamic and it is an static. So it is static, the always logic 1 is there, always, every moment. And why it is costly and why it is less density. Okay. We can design the SRAM using 4 transistors. Here we require how many? 6. It is costly. If you want to think about the cost, then we can also design this SRAM by using 4 transistors. In that case, you have to replace your PMOS by a very high input resistance, high impedance resistance. So we can say, we can design the SRAM by using 4 transistors instead of 6 transistors. In that case, we have to replace which one? The PMOS. So the upper one was my PMOS, if you can remember. So we can do some resistor here. But of course there is a drawback. The drawback is the power dissipation. So if you want no power dissipation, if you want more speed, you don't need to consider about the cost and the density, we should take the 6 transistor. So usually actually we use the 6 transistor one, but there is an option. If you want less transistor, we can just replace the PMOS with the 2 high impedance resistor. So you can design the SRAM. Okay. Now let's see how we can read and write in the SRAM. Okay? How we can read and write in the SRAM.
1 minute.
Yeah, sure.
I have a question. The upper one is the word line. Oh, this is VDD. This is different.
VDD for these MOS. Here, this connection, I need to correct this connection. So, the connection should be. Okay, let me give the connection properly. It's cross coupled, sorry.
That's a pass transistor, right?
Yeah. This is a cross coupled. So don't worry, I will upload this and notes here. You can see the figure.
Cross couple.
Yeah, cross coupled. So if this one is given to this gate, and this one is given to this gate. Cross coupled. Okay. So let's see about how we can do the read operation of the SRAM and the write operation. So if I just draw the simple one, simplified one. So we have this inverter circuit, then we have this inverter circuit, like this. Then we have this bus transistor here, excuse me.
Rest is connected with the ground, right?
Which one?
The last one that
Yeah.
you have.
Yes. This is very this ground. Yeah. So this is the bus transistor, and these two bus transistors are connected to the one line. Here we have the bit line bar. Here we have a bit line. Okay. So we are talking about read operation. So, of course, at first what do you need to do? We need to turn on both the pass transistor. We need to turn on both the pass transistor, so this bit line will be connected because you want to read the data, read the information from the memory. You want to take the data from here to bit line. So to get the connectivity, we have to make sure that both the pass transistors turn on. So to turn on the pass transistor, you have to apply the voltage at the one line. Okay. So by applying the voltage at the word line, both the pass transistor will be turned on. So you apply VDD here or some voltage here, then this transistor will both of them turn on. Okay. Once the pass transistor is turned on, then whatever voltage that is available at the point Q. So that means here we are feeling that we have logic 1 here. So it's logic 0. So logic 0, logic 1, right? So we can consider for logic 0 any volt or 2 volt or anything. So for example, we consider logic 0 equals to 2 volt and logic 1 equals to 2 volt, logic 0 equals to 0 volt. So we can consider a point here is Q and a node here which is Q bar. So when the transistor on, we have a whatever voltage at this node will be available for the bit line through this pass transistor. And whatever voltage is available at this node Q bar will be available at the BM bar, right? So whatever the voltage at Q bar will be available at BM bar, whatever the voltage is available at Q bar node will be available for the BM. Okay. Then by using the sense amplifier, we can sense the voltage at the bit line and can be the voltage. So again, then we can have some sense amplifier here. We can have a sense amplifier. Sorry. Then the question will become why we need both 2 bit lines. We can just get logic 1 here. Whenever we are getting logic 1 here, we will be getting logic 0 here because this is a bar. We are getting bar, so we have 0, so it is 0, so we get BL bar 0. Here we get BL equals to 2 volt, logic 1. Then why we need these 2 bit lines? We need 2 bit lines to improve or to increase the speed again. How? In that case, what they will do actually, they give it both the input to a comparator. So now if you look at here, if you want to measure, so it will be the bit line will be given some predefined voltages. For example, 1 volt. And here we have 2 volt here, right? For logic 1. So it will be increment from 2 volt, 1 volt to 2 volt. Similarly, here it will go from 1 volt to 0 volt because it is 1 volt predefined. But we need 0 volt, so it will go from 1 to 0 volt and it will go from 1 to 2 volt. So when it is going increment, it will become, for example, from 1 to 1.1 volt. And it is going from 1 to 0.9, 0.8, 0.7, so 0.9. These 2 voltage will be given here. And when it will be given here is 1.1, it's 0.9, so it will give you the output of the comparison. So you can see the trend of the increment or decrement. So from the trend, it can just select it's an incrementing, so it will just give you a logic 1 or logic 0. So it will not wait until to reach to 2 volt. It will not wait until to reach to 2 volt. It will just see the trend. So to see the trend, it will just take the 2 voltages here, compare it, and as it is an amplifier, it will just amplify and it will say that it's a logic 1. So this is how we can actually read the memory from the SOT. Okay. For the write operation, okay, for the write operation, so that means we have some data, either logic 0 or logic 1 in my bit line, and we just want to pass it to our memory cell, right? To the memory cell. So if we think that in the bit line we have 1, logic 1, that means in the bit line bar we have logic 0. And initially we have the pair in the inverter circuit we have 0 here. Initially we have 0 here. In the memory cell we have logic 0 here. Now we want to store logic 1 here. So when the pass transistor will be turned on, then the bit line voltage will be applied to the inverter. The pass transistor will on, then the bit line voltage will be given to here. But this one will try to store or try to reduce the voltage to logic 0. This one, this side. But at the same time, when we have a BL0, this will be also given here. Then this BL0 will come to here. And when this BL comes to here, this inverter circuit will give it to 1. And when this 1 will come here, it will give it to 0. So it will store 1. So it will be stored through this path into the memory cell. So as we can say that like this way, when the pass transistor is on, then the bit line voltage will be applied to the inverter circuit. But this inverter, the first inverter, this side, will try to reduce the voltage to bit line to logic 0 because it has already logic 0. It will try to reduce it. But on the other hand, the bit line bar is 0, which is given to the second inverter. This is inverter 1, this is inverter 2. If you just think about the CMOS, this will accept this 0 and will give it 1. And then when it is 1, so it will go to this here 1. So this first inverter now will give it output 0. So it will now become, it was previously 0, but it will become 1. In this way, we can store 1 in our right, 1 in the SRAM circuit. And here the SRAM doesn't have any capacitors, so it doesn't depend on any charging and discharging. The time, the speed is very high. That's why.
Why it tries to make it 0 here in the, and when the bit line is 1, once it passes?
So I think it's because, if I'm not wrong, because we have the NMOS, and MOS will not allow to pass logic. That's why. They didn't mention, but my understanding, because the NMOS will not pass logic high, that's why it will reduce to 0. They will pass logic 0. NMOS is good to pass logic 0. That's why the logic 0 will take the initiative to store 1 here. Okay?
So every time whenever we try to store information, it is from the BL bars.
BL bar. Okay? So this is all about this SRAM and the DRAM. So we already know the internal structures of SRAM, internal structures of DRAM, and how to write and how to read in the DRAM, and how to write in the SRAM. I hope you can understand and you can explain it properly, right? Any question for this SRAM and DRAM?
This is for which RAM?
This is static RAM.
Static RAM.
Yeah. We already done the DRAM. The DRAM is just consists of what? Only one transistor and
This is a static RAM.
capacitor. This is the static RAM. Yes.
This is also static RAM.
Yeah. So this is the static RAM. You can just replace this inverter circuit with the CMOS circuit. What is the inverter circuit? In the CMOS? Right? A PMOS and an NMOS make a CMOS inverter circuit. So here we have one. Here we have another one. You can draw another one here, like okay. Now it's clear. So this is both the structure for S1. And as I mentioned, we can design this S12 instead of 6 transistor. We can design also by using the 4 transistor. In that case, you have to replace this PMOS with the high impedance resistor. just replace your PMOS with a high impedance resistor. But in that case, the drawback is the power consumption, power distribution will be high. But you can reduce the cost, you can increase the density, but the power consumption of the power distribution will be high. It will get heat generated. On the other hand, the DRAM is nothing but a fast transistor and a capacitor just. This is the DRAM. Here also we have this word line. Here we also have the bit line. Here we have 2 bit line. Here we have only 1 bit line. Here we just need 1 transistor. Here we need 6 transistors. Here we don't need any capacitors. Here we need capacitors. So here the speed of read and write depends on also charging and discharging. Here it is not dependent on charging and discharging.
It stores the data.
That's why it's more faster. The SRAM is more faster. The fastest among all the memories. Okay. Another thing is it's a cache memory. It's a main memory. So as this is costly, we cannot design the main memory with the SRAM. It will take more. It will increase size as well as cost. So, but it is important so that we can use for as a cache memory. Right? We can use the information frequently. The processor use this cache memory so that we can take and give and forth and back for more frequently. Okay. Sometimes if you can, I think you know, all of you know, sometimes you need to refresh or you need to erase our memory from the cache. Otherwise, you can see your mobile getting slower and slower. So if you just go to the memory cell, see the cache, you just remove the cache, then it will again become more faster. Because they will not erase itself. You have to erase yourself. So if you just erase those cache, then it will become again faster.
And the cache memory capacity also generally will have less.
Sorry?
We'll have less cache memory in every electronic
Yeah.
device.
Yes. Because it's costly
Yeah.
and it's take more space. It requires 4 or 6 transistors. Okay? So now we'll talk about, so this is all about, we'll talk about the RAM and we'll talk about the ROM as well. Now I want to talk about another memory is known as flash memory. There are some advantages or disadvantages between this RAM and ROM, right? Some have the high, very fastest memory cell like a SRAM, but the capacity is small. On the other hand, the DRAM very not so fast, but the storage capacity is very high. In case of read-only memory, we can only read, we cannot write. Here in RAM, we can read and write. But if you look at the flash memory, it has all the properties. The flash memory has the properties of high storage capacity. Flash memory. The properties are, it has high storage capacity. It is non-volatile. That means it can retain its information even you remove the power. In system read and write capability.
What's volatile? I forgot.
So non-volatile and volatile means if you just turn off the power, if you remove the power, it can retain the information. That is known as
Non-volatile.
So in system read and write operation means in case of read-only memory, we cannot write, right? We just only read. Here it is capable to read and write. It is the very first operation, cost effective and high density. So this flash memory have all these properties. So if we just want to see how this flash memory actually, we can construct the internal structures. A single transistor cell flash memory is look like we all know about our MOS capacitor, right? A MOS, metal oxide semiconductor. In the metal oxide semiconductor, we already know it has a 3-terminal device. It has a gate terminal, it has drain terminal, it has source terminal. Here, they mentioned this in flash memory, it constructs with a MOS capacitor which has an additional terminal, or they call it a floating gate. In addition to the gate, control gate, drain terminal and the source terminal, they just mention it as a floating gate. In my understanding, it is actually nothing but the channel. We already know, whenever you apply some gate voltage, the channel will be formed. When we don't apply any gate voltage, the channel will not be formed. That means you are trying to design this flash memory by using an E-MOSFET. Whenever you have an E-MOSFET, whenever you apply sufficient gate voltage, a channel will be formed, right? So in case of E-MOSFET again, we have an N channel and P channel. This is nothing but an N channel E-MOSFET. That means electrons are there. So, but here in this reference book, they named it as a floating gate. This is a gate, control gate. We know in a MOS, this is a gate terminal, this is the drain terminal, this is the source terminal. The drain terminal is connected to VDD, the source terminal is connected to the ground. So, these charges just near to the gate terminal, they named it as a floating gate. So, this is a single transistor cell in a flash memory. Here, if you look at this area, if I just draw this area separately, we can see if we have a huge amount of charge carriers, this is for storing 0. If we have this one, the same, this is drain, this is source, this is gate, and this is the floating gate. If this floating gate area have less charge, this is they call store 1. See, if you can remember the structure of the MOS, is nothing but actually the channel. In the channel, we have negative charges. So as we have a negative charges, it's nothing but the N channel E-MOSFET. Okay. So this is the primary thing. So here the MOS transistor consists of a control gate and a floating gate. The floating gate stores electrons or charges. Floating gate stores electrons as charges as a result of sufficient voltage applied to the control gate. So this is the same thing. Once you apply the gate voltage, the channel will be formed. So channel formed means there are sufficient negative charges, so electron charges. So A0 is stored. Now if you are talking about the bits, either logic 0 or logic 1. A0 is stored when there is more charges. A0 is stored, you can see here. A0 is stored when there is more charges. A1 is stored when there is no charge or very less charges. So to store 0 means more charges in the floating gate. Store 1 means less charge or no charge in the floating gate. That means there is no channel. Store 1 means, okay? Fine. The amount of charge present on the floating gate determines if the transistor will turn on and conduct the current from drain to source during the read operation. Store means what? Write. So if you want to store 0, there will be sufficient charges. If you want to store 1, there will be less charge or no charge. Now, amount of charges in the floating gate determine whether the transistor will turn on and conduct the current from drain to source during the read operation. Let's see the read operation and write operation, then it will be very easy to read. If we want to see the operations of the flash memory, there are three different operations. One is known as write operations. They are also named as programming. Programming means the write operation, you just program. Then we have a read operations, and the third one is the erase operation. If you want to erase, if you have to remove, if you have to replace your information, so that is known as erase operation. So there are three operations: write operations or programming, read operations, and the erase operation. So for the write operations, if you want to do the write operation, at first you have to make sure that in the previous stage we have erased all the information of each cell. This is only one cell information, so it will be an array. We have to erase all the information. That means we have to remove all the charges. In our previous erase operation, we have to erase all the charges. So if you want to remove all the charges, what does it mean? It is storing 1, because no charge or less charge means store 1. So during the write operation, at the very beginning, we have all ones. We have all ones. Now you have to apply a sufficient gate voltage here with respect to source. So what will happen? So that means there is no charge at first, right? We are talking about write or programming operation. So at the very beginning, there is no charge. In the previous erase operation, we already removed all the charges from all the cells. So that means no charge, and less charge means store 1. So in each and every cell, we have now logic 1. Now you have to apply a sufficient gate voltage, a rewrite. What will happen? As we are applying a positive gate voltage, it will attract electrons. It will attract more electrons from here. So electrons will be gathered here. You have to apply a sufficient gate voltage so that it can attract more electrons here, so that we can restore 1. To restore 1, what you need to do? Apply sufficient gate voltage with respect to source. Same, which is the channel is formed actually. It's nothing but we're just creating the channel actually. Right? We are just creating the channel. Okay. If you don't want to store, if you want to store 1, we will not apply any gate voltages there. Okay. So this is how we can store 0 and store 1. That means write or programming operation. And now about the read operations. During the read operations, again we apply positive gate voltage here. Every time we are applying the positive gate voltage. Here again also now we call it V-read. Now what will happen? Here also we apply V-read. Here we have logic store 1. Here we have stored 0. As I mentioned, the amount of charge in the floating gate determines whether your transistor will turn on and conduct the current from drain to source during the read operation, right? So now the storage is there. You have store 0, you have store 1. Now you want to retrieve your information. You have to read. So now when you apply the gate voltage here, you don't need to apply a very sufficient amount of gate voltage. Just small amount of gate voltage. But here you are applying positive gate voltage, but this is a negative charge and a huge amount of negative charge. So it is not easy to turn on this transistor. It requires more and more gate voltages. So if the transistor is not turned on, so there will be no channel formed, there is no current flow from drain to source. On the other hand, here we have only few negative charges. Now whenever you apply a very small amount of positive gate voltage, it is easily turned on. And when this transistor will turn on, a current will flow from drain to source. So we can say the presence of the current is sensed to indicate 1, and the absence of the current to sense indicate 0. Clear? Here we have huge amount of charges. Now to turn on, it requires more and more voltages. So it seems that we cannot turn on this transistor. And when the transistor is not turned on, we cannot have a current here. And here we require only small amount of threshold voltage to turn on. And when there is a turn on, we have a current here from drain to source. So when there is a current present, it can sense as a logic 1. When it will sense an absence of current, it will give you logic 0. So this is the read operation of our flash memory. Now, as I mentioned, every time we need to erase the information to reprogram it. To erase this one, what you need to do, you just need to apply your voltage to the source terminal with respect to ground. That means ground at gate at 0 volt. Now you have to give the higher potential the source terminal. Now what will happen? This positive terminal will attract these electrons. So electrons will come here. So it will clear the floating gate. These are the charges, right? Negative charges. You have to attract. You have to take out all the negative charges here. So you have to give the source terminal, the gate voltage, the positive voltage to the source terminal with respect to the gate terminal, VGS. So it will be VSG. Then this terminal will attract all the electrons, and these electrons will get out from it. So this is the erase operation. So, yeah.
So to apply VSG, do you put a negative voltage on the gate instead of a positive?
It's actually not a negative voltage. It's actually, you can think like a higher potential. So it is a potential difference, right?
Okay.
So VGS and VSG is nothing but a potential difference. VGS means what? As I mentioned, VG minus VS. So gate terminal is at higher potential than the source terminal. VSG is just opposite. That means your source terminal is now at higher potential. So if you think this is 0 or ground, now here we have applied 2 volt. So here at that potential it is 2 and this at 0. Or you can say this is 1 volt and here you have 4 volt. This is at higher potential. If you apply 5 volt, for example, it can be easy to understand. Whenever we apply, if you can remember, in the common base configuration, right? So in a common base configuration, EBC, right? So we apply the forward bias here. This is NPN transistor. So we just said that this is the forward bias, right? N to N, P to P. So this is forward bias, and this base connection should be in reverse bias. So this will be plus to minus. So look at here. This is negative. This is positive to the base. So what does it mean? It means here this N is at higher potential than this one, and this one is lower potential. So in this perspective, maybe it is at 3 volt. In this perspective, it is 3 volt. Then you have to apply 5 volt here. So it is 5 volt. It is 3 volt. So it is at lower potential. But again, it is 3 volt. It is 1 volt. So it's a potential difference.
You could say reverse bias.
Yeah.
Gate then versus.
Here, look at here. This one, with respect to this one, this is reverse bias. With respect to one, this is forward bias. This is the same node. So it's supposed to be the same voltage. So if you apply 3 volt here, so it should be at higher potential. So you can apply 5 volt here, like this. So potential difference is 2 volt, 5 minus 3.
Can you explain one more time? Like this, I got confused.
Okay.
Sorry.
No, it's fine. So what I'm trying to is, I'm just trying to explain this one. As she asked me,
Yeah,
is it
explain
connected to
this.
the ground or not? So it is not always like that. You have to connect it to the ground. So this is called a potential difference. That means one node will be at a higher potential, another node will be at lower potential. That's
So
it.
which one is the higher potential?
Here to erase, the source should be at higher potential and the gate should be at lower potential. Source should be at higher potential and gate should be at lower potential.
But gate is connected with the ground.
So yeah, that's right. So that means what? If you think about a battery, right? What does it mean? If you apply 2-volt battery, what does it mean? This terminal has 2 volt, this terminal has 0 volt. That is a potential difference. Right?
So S has higher potential,
Here, to erase.
but
During the
S is
erase-
connected, S is 0.
No, no. So if I draw this one like this only, okay? So this is gate, this is source. Usually what we do, we just do like this. The source is grounded and gate. Apply some positive gate voltage. So you apply positive, sufficient positive voltage, we store 0. Now you have to erase. During that one, you have to just change the polarity. Change the polarity. Now, you have to just change the polarity here.
No.
So what I am trying to say here that this negative potential is not always meaning to the ground. It sometimes can be just potential difference. So that's why I just draw this one for the common base configuration. It's an NPN. So this should be in forward bias. So that's why we connect in this way. Right? End to end, P to P, forward bias. Here it's supposed to be reverse bias, P to N. So here, the base terminal, here at positive, here at negative. What does it mean? It means this one is at lower potential, that's it. You just choose the same potential, same voltage here. So if you think that this is 3 volt, this is 3 volt, then if you just 5 volt, so it will be at a high potential. Okay? Like this. So this is all about flash memory. We have done the memory. We'll talk about a little bit more about the memory in next class on Thursday, right? And then next week we'll talk about the PLA and PL. Okay.